Hello students, welcome to EPG Pathshala Biophysics. I am Dr. Ravi Majumdar, Emeritus Professor, Department of Natural Sciences, West Bengal University of Technology in Kolkata, and formerly I was Professor and Head, Biophysics Division, Shah Institute of Nuclear Physics in Kolkata. Today we will talk about particles in rectangular potential wells and quantum dots. Name of the paper, as you all know, is Quantum Biophysics. What are we going to learn from today's lecture? These are solutions for energy levels and wave functions, probabilistic interpretation of wave functions, quantum dots with practical applications, and particle in a box in 3 dimensions. Why do we talk about rectangular potential wells? Electron in a rectangular potential well is a simpler version of an electron in hydrogen atom. Electron is confined to small region in both cases. It is easy to solve Schrödinger equation in this case and check all the typical features in quantum mechanics, such as the discrete energy levels and the probabilistic description of electron's position within the well. The rectangular well should not be treated merely as a model system. We shall see that it has wide practical applications as well. Well, just to give a few examples, these are electrical and thermal properties of metals based on free electron theory, and then optical properties of biologically important linear molecules based on pi electronic energy levels, which are like free electrons, and finally, designing of semiconductor nanomaterials like quantum dots. In all cases, the electrons in a rectangular potential well is the basic component.
Let us now come to the objectives of this lecture. Number 1, the energy levels and wave functions for electrons in an infinitely deep rectangular potential well are obtained by solving the Schrödinger equation. Then, the probabilistic interpretation of the wave functions and the meaning of normalized wave functions are discussed. Square of the normalized wave function gives the probability density or the probability function for finding the electron at a given point. Then we come to quantum dots. Quantum dots are usually semiconductor crystals where the electrons are trapped in a deep rectangular well having typical size of L of the order of 10 nanometer. That's the width of the potential well. It emits different colors depending on its actual size and temperature. Then an electron confined in a finite potential well can be observed outside its classical boundaries, though with a very small probability, even if it doesn't have sufficient energy to jump over the barrier classically. This doesn't happen in the case of infinitely deep potential well, and this happens only in the case of finite potential well. And finally, the energy levels and wave functions of the particle in a box are obtained as an extension of the theory to 3 dimensions. Basically, as I said, we are going to talk about an electron which is trapped or confined in a one-dimensional potential well. So this diagram shows the potential well. Electron is confined in a linear region along the x direction from x equal to 0 to x equal to L. And inside the well, the potential is 0. And outside the well, there is a finite potential V equal to V0. But since we are considering an infinitely deep potential well, so we'll put V0 tending to infinity. So let us consider an electron confined in linear space. In Bohr model, we found that an electron confined in a hydrogen atom exhibits discrete energy levels. In the case of an electron confined in a linear space, it's simpler to solve the Schrödinger equation. So we write down the Schrödinger equation, d square psi dx square plus 2m by h square times E minus V psi equal to 0. Well, we'll solve this Schrödinger equation to see that the same is true for an electron confined in a small linear region L which has atomic dimension of 0.1 nanometer or 1 angstrom unit. So let us write down the deep rectangular potential well of width L, see how it looks like. So we have V equal to V0 for x between 0 and L inside the well. As I showed in the last figure, that there is no potential inside the well and the electron is free to move inside the well. And V0 is infinity when you are outside the well, that is when x is less than 0 or x is greater than L. Now, since the electron is free inside the well, where V is 0, the equation inside is t square psi dx square plus 2me by h cross square psi equal to 0, well, where we have put V equal to 0. Or I can write this as d square psi dx square plus k square psi equal to 0, where k is 2me under the root by h cross, and k is actually the wave number, which is 2 pi by lambda, where lambda is the de Broglie wavelength of the electron. Now the solution inside is psi x is equal to a sine kx plus b cosine kx. Well, this is a second order differential equation, so two constants a and b. So a and b are constants to be determined from boundary conditions. Well, if you want to satisfy that this is the solution of the equation, then you can check by differentiating twice that this equation satisfies the Schrodinger equation inside the well. Now, the equation outside is d square psi dx square plus 2m by h cross square times E minus V0 psi equal to 0, where V0 is the potential outside the well. Now, in general, for E less than V0, this gives exponential solutions. In the special case of V0 equal to infinity, however, psi is 0 everywhere, since the product V0 psi must be finite at all points. So we need not solve this equation if V0 is infinitely large, because in that case, all that we need is V0 psi must be finite in order to keep the equation finite. So if V0 psi is finite, then psi has to be 0 at all points. The solutions inside and outside must match at the interface for continuity. Thus, the solution outside provides the following boundary conditions for the solution inside. That is, psi is equal to 0 at x equal to 0 and psi equal to 0 at x equal to L. So the first boundary condition gives b equal to 0, so that psi is equal to a sine kx. This is obtained from one of the boundary conditions, the first one, and the second boundary condition gives sine kl is equal to 0, that is at x equal to L, this right hand side should be equal to 0, so this gives sine kl equal to 0, assuming of course that the constant a is non-vanishing. So this gives k equal to n pi by L, where n is equal to 0 or an integer. Now, this equation k equal to n pi by L gives discrete energy levels, since k is related to the energy by the equation k equal to 2me root divided by h cross. This is how k was defined. So if you put this on the left-hand side of the last equation, k equal to n pi by L, then the allowed energy levels of the electron are obtained immediately. So these are E is equal to n square h square upon 8m L square, where n is an integer. Well, we shall see that n is a non-negative integer, and the corresponding wave functions are psi is equal to a sine n pi x upon L, since you are putting k equal to n pi by L. So these are the two important solutions. So one is gives the discrete energy levels, and the second equation gives the corresponding wave functions. Well, we still have an unknown constant a, about which we'll talk a little later. So now we come to the probabilistic interpretation of the wave function. Well, it's from this consideration that we fix the constant a. The intensity of the electron wave psi square is proportional to the probability of finding the electron at a given point x. This is because the particle is more likely to be found at those points where the wave describing it is more intense. Actually, psi square. Well, here psi is real, so you don't have to write psi star psi. Psi square, well, this describes the intensity of the wave. So I'm repeating that, you see, this is because the particle is more likely to be found at those points where the wave describing it is more intense. Then the next point is that since x is a continuous variable, psi square x is defined as the probability density, it's also called the probability function, at the point x, so that psi square dx is the probability of finding the electron at the point x, which means that between x and x plus dx. For actual probabilistic interpretation, the total probability of finding the electron between minus infinity to plus infinity should be equal to 1. But actually here, the electron is confined between 0 and L. So in this integral, that is psi n square dx integral is equal to 1. This means that the total probability must be equal to 1. The limits I have put is minus infinity to infinity. But you see, ultimately, these limits can be changed to 0 to L because the electron is present only in this region inside the well. So you have put the value of psi n square, which we obtained. And then if you put this integral equal to 1, then this integral can be solved from the by using standard tables, and it is found that the integral is L by 2 for all values of n. So this gives, the value of a square becomes equal to 2 by L, which means that the value of a is 2 by L under the root. So that is how we have fixed the constant a from the probabilistic interpretation of the wave function. So finally, we could write down the wave function in terms of known quantities because L is the length or the width of the potential well. So this is called the normalized wave function, and this 2 by L under root is called the normalization constant. The sign of the constant a is unimportant as it doesn't affect the probability function psi square. The negative integers for n are ignored as they merely change the sign of the wave function psi, which is of no physical consequence. Also, n equal to 0 is ruled out as it gives psi is equal to 0 everywhere. Thus, the acceptable quantum numbers are n equal to 1, 2, 3 and so on, where n equal to 1 describes the ground state of the electron. So, in short, n is a positive integer, 1, 2, 3 and so on. So based on this probabilistic interpretation, the electron is pictured as a smeared out charge or a charged cloud between x equal to 0 and x equal to L, where E psi n square dx gives the charge at any given point x, so that the total charge is obtained by integrating E psi n square dx, and if you integrate this, well, since the wave function psi is normalized to unity, so the value of this integral becomes equal to E, which is the total charge of the electron. So in quantum mechanics, you do not view the electron as a point object. Well, it is viewed as a smeared out charge or a charge cloud, you see, between the points x equal to 0 and x equal to L, that is the region where the electron is confined. Let us see that the wave function, standing wave patterns for the electrons for the various values of n. So if you put n is equal to 1, then the wave function is psi 1 equal to 2 by n under the root sine pi x by L. If you put n equal to 2, then you get 2 by L under the root. So you put n equal to 2, so you get sine 2 pi x by L. Now, you can see that psi 1 has nodes at x equal to 0 and x equal to L, because if you put x equal to 0, then sine 0 is 0. And if you put x equal to L, then you get sine pi, which is also equal to 0 in the first equation. So in either case, psi 1x is equal to 0. So that is why I repeat that psi 1 has nodes at L equal to 0 and x equal to L. And the maximum it has at the point x equal to L by 2, because if you put x equal to L by 2 in the first equation for psi 1, then you get sine pi by 2, which is equal to 1. So it has a maximum value psi 1 at x equal to L by 2, which is in the middle of the potential well. One of the figures is the figure 1 shows L equal to pi by 2, and figure 2 shows 1 bump, because you see in figure 1 we plot the wave function psi1, and in figure 2 we plot the wave function psi1 squared, which is the probability function. Now we come to psi2. Now you see from the same argument we find that psi2 has nodes at x equal to 0, L equal to 2 and L, and maximum or minimum in between these nodes. So the figure 1 shows L equal to lambda or 2 lambda by 2, and figure 2 shows 2 bumps. That's the probability psi square. It shows 2 bumps and so on. So in general, L equal to n lambda by 2 or lambda equal to 2L by n. So using lambda equal to h by p and p equal to 2me under the root, you can check that E equal to n square h square by 8 ml square. And there's discrete energy levels which you actually found by solving the Schrodinger equation. Actually, when I was talking about these things, I didn't show the figure because the figure 1 and 2 actually appears after this. So you can now see the figure 1 and the figure A and figure B, which I was talking about. These are the picture of the wave functions, that the wave function has nodes at the 2 points in all these 3 cases, and for n equal to 1, that is ground state, lambda is 2L, and then lambda is equal to L, and then lambda is equal to 2L by 3, and so on. And when you talk about the probability functions, then probability function or the probability density is square of the wave function, and therefore it doesn't have any negative value. So if you square up the previous curves, then you get 1 bump, 2 bump, and 3 bumps like that. So this is how the probability function looks like for the various states, n equal to 1, 2, and 3. So now we come to the orthogonality of the wave functions. Well, we have seen that the wave functions are normalized to unity, but there is an additional property of the set of wave functions psi n. This property tells us that these wave functions are orthogonal to each other. So in the present example, this means that for m not equal to n, see psi n star, psi m dx, is equal to 0. So you can check this by putting the appropriate wave functions. If you put psi 1 and psi n equal to 1 and m equal to 2, if you put those functions, for example, then this becomes equal to 0. So you can satisfy yourself by putting different wave functions that this condition is satisfied. Okay, but if you put the same wave function, then this will give you the normalization condition. So the two conditions can be combined to write down this integral psi n star psi m dx. This integral is equal to delta nm, where delta nm is called the Kronecker delta function. That is, if n is equal to n, then this is 1. So that gives you the normalization condition. But when m is not equal to n, then this gives 0, which means that the orthogonality condition. This integral has been expressed as, psi n psi m within brackets. This is a conventional way of representing the integrals. As we have used the bra and ket notations for the integrals. So when you write, you see psi n and psi m within a bracket like this, it means that this is an integral where the first quantity psi n has to be starred, that is the complex one, and then psi m has to be unstarred, okay, assuming that both are complex quantities. So if you integrate this, you get delta nm. So psi n and psi m, these are of course real in our case. Okay, for the sake of generality, we have assumed that these are complex, and so we have put start quantity in the first of these wave functions under the integral. So now we come to the average of an operator. So how do you define the average of an operator? Once the probability functions psi star psi is defined, it can be used to calculate averages in quantum mechanics. One of the postulates of quantum mechanics is that the average or the expectation value of an operator is, well, this is the notation for the average of an operator, which is also called the expectation value. So this is equal to an integral where the operator A is sandwiched between psi star and psi. Of course, as I said, in our case, psi is real, so psi star and psi, they are just the same, okay? You don't have to write star. So there's psi star and A psi. Well, as I said, that A is an operator, so it matters a lot whether you write A in the beginning, in which case the operator will operate on both psi star and psi. If you write A in the middle, it operates on psi. So, you see, the postulate of quantum mechanics says that, you see, psi has to be written, this operator A has to be written in between psi star and psi. So that's what I've said, where the operator must be placed between psi star and psi in general, so that it operates only on psi, which follows the operator. Now, the only justification for writing this is that, you see, this works well. That is, the result based on this agrees with our observations. And then let us take an example. That is, let's find out what is the average of a Hamiltonian operator. So we can see that the average of the Hamiltonian operator is psi star h psi integral. And if you operate h on psi, well, h, since it's in the middle, so it operates on psi. So if you operate h on psi, the Schrodinger equation written at the end gives you E psi. So for h psi, you write E psi, and E being a number, you can take it out of the integral, and what remains is the integral psi star psi dx. And since psi is a normalized wave function, so that integral should be equal to 1. So the average of the Hamiltonian operator is the energy. So you see, the energy is something which is real and measurable. So operators having real averages are called Hermitian operators or real operators. Now, in obtaining this relation, we have used the Schrodinger equation, as I said, h psi equal to E psi, and the normalization condition of the wave function, which I have already explained. Now, let us check that the ground state energy level for an electron in a rectangular potential well is given by this integral, that is h1 psi 1 h psi 1. See, so let's check that gives the ground state energy. So according to what we wrote in the previous slide, so E1 is equal to the integral of psi 1 h psi 1. So that's what we have written. So psi 1 is, that's the wave function. You have taken the normalization factors outside, and here you have sine pi x by L, putting n is equal to 1. So this is the wave function, this is psi 1. And then you write the Hamiltonian operator, which is, h cross square by 2m, which you take out of the integral. These are constants. And inside you have d square dx square. So Hamiltonian operator is written in the middle, and you see this differential operator, which is contained in the Hamiltonian, will operate only on the wave function, which is written after the operator h. So this wave function is again psi 1. So I have written sine pi x by L, putting n equal to 1. So if you differentiate sine pi x by L twice with respect to x, then you get, you see this 2 by L, then h cross square by 2m, then pi square by L square, and within the integral you only have, you see, sine square pi x by L, the integral of this. Now, while obtaining the normalized wave functions, we found that the value of this integral on the top is L by 2. So if you write this integral, if you put this integral equal to L by 2, well, then you get the E1 equal to, put it equal to L by 2. So you see, one of the L's will cancel, and so you get E1 equal to h square by 8 ml square. Now we know that this is the correct result because this is obtained by putting n equal to 1 in the expression for the discrete energy levels, which we have obtained earlier. Now the same may be checked for the other energy levels as well, you see, by using the appropriate wave functions. If you put psi 2 instead of psi 1, you will get E2. If you put psi 3 instead of psi 1, you get E3. So you can check that all the energy levels, you see, they agree with our general result. So this is a very important thing, that if you take the average of the Hamiltonian operator, you get the energy. You see, the energy levels are measurable quantities. The Hamiltonian operator is a real operator or a Hermitian operator, which we have already mentioned. Okay, now we talk about the energy gaps and the absorption wavelengths. Well, obviously the energy levels are not equally spaced because you have n square on the top. So in a rectangular potential well, the energy gap between two successive energy levels n and n plus 1 can be obtained by subtracting En from En plus 1. So that's the value of delta E. That is the energy gap between any two successive energy level. If you put n equal to 1, this energy gap will be between E2 and E1. If you put n equal to 2, then this energy gap will be between, you see, the third and the second level, and so on. So in general, if you subtract, you see, En from En plus 1, then you get 2n plus 1 h squared divided by 8 ml square. So there are a few things to note here. Note that the energy gap is significant only for a particle like electron having such a small mass confined to a small length of atomic dimension. So we take L equal to 1 angstrom, see, which is approximately the size of an atom. So if you take this value, then the energy gap between the ground state and the first excited state for the electron is 113 eV. So you can check this by putting n equal to 1 in the equation, which is shown on the screen. So delta E will be E2 minus E1, and if you put n equal to 1, you get the value of the energy gap between the ground state and the first excited state, and this will be in joules. So if you change joules to electron volts, then you can check this energy gap is 113 electron volts. So this is about the gap, and then we come to the wavelength. The wavelength lambda absorbed by the electron in jumping from the ground state to the first excited state is obtained by equating the energy gap to hc by lambda. Well, we have done this in the case of hydrogen atom also under Bohr model. So if you do that, then you can find out, you see, what is the absorption wavelength for the electron when it jumps from the ground state to the first excited state. So this turns out to be 110 angstrom. The next point is that if a rectangular well like this, if it contains 10 non-interacting electrons, I am particularly saying non-interacting electrons because you see, when you put more than one electron, then they will repel each other, and you see that will, you see, disturb the energy levels. You see, so I'm assuming that the electrons are non-interacting. So in a rectangular well, if a rectangular well contains 10 non-interacting electrons, for example, they fill up the first 5 energy levels, because each energy level can accommodate 2 electrons with opposite spin, which you know. So the characteristic absorption wavelength is due to an electron jump from the highest occupied level, in this case it is n equal to 5, to the lowest unoccupied energy level, which is n is equal to 6. Let's take an example. Now this happens in the case of vitamin A, or the retinol molecule. You can see the picture of this molecule in the figure. This molecule has a linear chain consisting of 10 carbon atoms, now each contributing a free pi electron. Well, we'll talk about pi electron later, but for the time being, well, you assume that this is just a free electron. So it's a linear chain of 10 carbon atoms, so there are 10 free electrons which are confined in this chain. So I say that 10 pi electrons are confined to the linear part of retinol. Well, and this can be viewed as 10 free electrons in a rectangular potential well, whose width is, you see, 10 minus 1, it has got 9 bonds. So the width L should be 9 times the average carbon-carbon bond length of 1.4 angstrom. The average carbon-carbon bond length is 1.4 angstrom. Actually, the single bonds are a little longer than the double bonds, but the average is 1.4 angstrom. So if you multiply this by 9, then you get, you see, the length of the rectangular potential well. So you can find out L in that way. So in reality, however, L is less due to zigzag nature of the bonds, for which corrections can be made. Since the first 5 energy levels are occupied, we may put n equal to 5 in the formula for energy gap and calculate the wavelength for transition of a pi electron from the level n equal to 5 to n equal to 6. The result is in good agreement with the observed characteristic absorption wavelength of the vitamin A molecule, which is about 3750 angstrom unit or 375 nanometers, and this is in the ultraviolet or UV region.
One of the important developments in recent years is the fabrication of quantum dots. As the name suggests, a quantum dot consists of a particle ideally confined to a point or a zero-dimensional space. Obviously, in real life, such a situation cannot be realized. So, the size of a quantum dot is obtained by assuming that the particle is confined in a deep rectangular potential well, and finally reducing the size of the well to a small but finite cutoff value, which is about 10 nanometers, as we shall see. We shall also find that a quantum dot emits different colors depending on the size of the well and the temperature. This makes it useful for practical applications such as biological markers and so on.
Well, now let us come to what is known as quantum dots. Now, a recent development in nanotechnology is the fabrication of quantum dots. As the name suggests, a quantum dot consists of a particle ideally confined to a point. Now, as I said, in practice this cannot be achieved. So the size of a quantum dot is obtained by assuming that the particle is confined to the region x between 0 and L, that is the rectangular well, and finally reducing L to a small but finite cutoff value. Now, how do you obtain this cutoff value? You can see on the screen that this is done by requiring that the energy gap delta E between the first two levels of a rectangular well must substantially exceed the energy kT at absolute temperature T, where K is the Boltzmann constant. Because you see, why kT? Because you see, kT is approximately the average, you see, energy of particles at room temperature if you put T equal to 300 degrees. Okay, so you have delta E, that is the energy gap E2 minus E1, which turns out to be 3h squared divided by h ml square, and we want that this should be, you see, much larger than kT at temperature T. So you can write this equation as L much less, L has to be, the width of the potential well has to be much less than under root of 3h squared divided by 8m kT. So this is a practical condition for the quantum dot to work. So L is approximately equal to this, what I have written on the right hand side. Then this gives the critical condition, which is written on the next slide. So you can see here that the cutoff value of L is taken to be LC of the order of 3h squared divided by 8m kT under the root. Now, you see, for the electron, if you put the mass is equal to 9.1 into 10 to the power minus 13, 1 kg, and if you put T equal to 300 Kelvin, then this size you can check by putting these values and put the value of Planck's constant, and you find that this size LC, that is the critical length or the cutoff value of the potential well, that turns out to be about 6.5 nanometer. You see, of course, this value, you see, it increases or decreases, you see, depending on the temperature, but at room temperature it turns out to be about 6.5 nanometer. So you see, this is something like a point. You see, when we talk quantum dot, I mean that you see, you're talking about a rectangular potential well which has a very small width of about 6.5 nanometer, or roughly speaking, you see, about within, you see, 10 nanometers. So this is the typical length of a quantum dot. The next point, the size controls the spacing of energy levels of the electron. As a result, the quantum dots emit different colors of light depending on their size. So this makes them suitable as biological markers. And then finally, the commonly used quantum dots are nanometer-sized crystals of some semiconductors which are able to trap electrons in small regions of about 10 nanometer. So what I mean is that, well, if you sort of vary the size, the length, you see from 6.5 nanometer, if you change it, you see to some value between 0 and 10 nanometer, then you can get different colors of light which are absorbed and emitted. This makes quantum dots very important in practical biology as well as in the industry. Now there are a few things which we wanted to describe, that if you take a finite potential well, instead of an infinitely deep potential well, which is shown on the right, well, these are the results which we have already obtained. You see, for an infinitely deep potential well. But on the figure on the left-hand side, this shows a finite potential well where V0 has a finite value and not infinity. Well, if you cut off V0 to a finite value, then you see, then the wave functions will look like what is shown on the left-hand side of the figure, as you can see. So let me just read out what is written on the screen. The wave function psi x no longer vanish at the boundaries. These are finite at boundaries, and the exponential decay outside must match the periodic solutions inside. Finite well has lower energy levels, and penetration of wave functions into classically forbidden region suggests that even though the electron doesn't have sufficient energy to jump across the barrier, because the energy of the electron is less than V0, that's what we are assuming, well, the electron cannot jump across the barrier, but it can leak through it. So this is a typical property of a particle like electron in quantum mechanics, because as I said, as you all know by this time, the electron in quantum mechanics is represented by a wave, and when the electron behaves like a wave, well, the wave has a small but finite probability of leaking through the barrier, as you can see. So this leakage through potential barrier is a very important phenomenon, and we'll find more examples of this in the coming lectures. And finally, we talk about the particle in a box. That is, we extend our considerations to 3 dimensions. So this is a case where a particle like the electron is confined in a cubical potential box of dimensions L with infinitely large potential barriers outside. You see, we are considering infinitely deep cubical potential well, or a cubical potential box. So in this case, there are 3 quantum numbers. You see, one for each dimension, that is nx, ny, and nz. In Cartesian coordinates, you have 3 dimensions, so 3 quantum numbers. The energy levels and the normalized wave functions, you see, these can be generalized. You see, the energy levels can be obtained by adding the 3 energy levels, you see, for x, y, and z directions. So E is equal to h square upon 8ml square, nx square plus ny square, and nz square. And so the energy levels are obtained, you see, by putting different values of nx, ny, and nz. And the wave function, on the other hand, you see, can be obtained by multiplying the wave functions in each dimension. You see, this follows from the probabilistic interpretation of the wave function. You see, psi x, y, z is the product of the 3 wave functions, sine nx pi x divided by L, that is psi in the x direction, and then psi in the y direction, and then psi for the z coordinate, okay? So you get, and 2 by L to the power 3 by 2 is the normalization factor, root 2 by L coming from each dimension. So this is the value of the wave function. So you get the energy level and the wave function. Note that except for the ground state level, you see, all the other energy levels are degenerate. The ground state level can be obtained by putting nx equal to ny equal to nz equal to 1. So that gives the lowest energy level. But you see, if you consider the other energy levels, that the energy levels of the excited states, then those are all degenerate. For example, the first excited level can result from any of the combinations, that is nx equal to 2, ny equal to 1, and nz equal to 1. The second combination is nx equal to 1, ny equal to 2, and nz equal to 1. And the third combination is nx equal to 1, ny equal to 1, and nz equal to 2. So each combination will give you the same energy level. So that's why you say that we get degenerate energy levels. And finally, let me mention that the particle in a box problem, this is the problem which we are talking about, has important applications in modern science, such as the free electron theory of metals and the resulting electrical and thermal properties. Well, actually those who are involved in material science research, see, they know the importance of the application of this formula.
Let us now summarize what we have learned in this lecture. Energy levels and wave functions for electrons in an infinitely deep rectangular potential well have been obtained by solving the Schrödinger equation. Square of a normalized wave function gives the probability density for finding the electron at a given point. Quantum dot usually consists of a semiconductor crystal where electrons are trapped in a deep rectangular well having a typical size of the order of 10 nanometers. It emits different colors depending on its actual size and temperature. An electron confined in a finite potential well with insufficient energy to cross the barrier can be found outside its classical boundaries. And finally, the energy levels and wave functions of a particle in a box are described as an extension of the theory to 3 dimensions. Thank you.